All right, on the first day when we were doing this, we took, this is Unit 1, Lesson 10, Practice Problems. And we talked about on these first three examples, I can do rigid transformations to make triangle ABC land on triangle A prime, B prime, C prime. But when we tried that down here, we could get the vertex lined up and we can get the sides lined on the same rays, but they weren't the same triangles. One was bigger or smaller. So we would have to do a dilation in order to get one triangle to coincide or be on top of the other triangle. So this last section is talking about the properties of similar triangles. So if I have two triangles that are similar, and I'm not going to draw, oh, I'm sorry. Oh, you didn't see that at all, did you? All right, let me back that up again. I'm sorry, my screen was frozen, guys. Yeah, that's okay. All right, so we were, what I was saying is we were working on these, this on our very first problem, and we would say on these first three, I could do rigid transformations to get triangle ABC to land on top of triangle A prime, B prime, C prime. On all three of these, I could complete a rigid transformation statement that would say that. So these triangles in these first choices would be congruent. But when we tried this with option D, we could move A on top of A prime, and we could line up A, B, and A prime, B prime. Let me draw that on some patty paper. So if I wanted to move this triangle, I could translate triangle ABC along the directed line segment from A to A prime. So maybe right here. And then maybe I would need to rotate. So I could rotate so that AB is on the same ray as A prime, B prime. But we can see that one triangle is bigger than the other. So we said on this particular example, we would say we would now dilate the image of triangle ABC with the scale factor of whatever this big side is, B prime, C prime, whatever that length is, the new length, over that original length, BC. So we said if we could describe the transformations and include maybe dilations, then those triangles would be similar, okay? And congruent triangles all are similar. Remember that scale factor is 1. So there are some important properties, and I'm just going to draw one that's pretty simple. So I'm going to just draw any triangle. I'm sorry. Got my screen all over the place today, don't I? So I'm just going to draw a triangle. Doesn't really matter what shape that triangle is. And this will not be drawn to scale. I'm going to make a segment over here that is E and F. And these two sides are going to be parallel. All right, these triangles would be similar because in parallel lines, we would have the corresponding angles here and here to be congruent. And if you wanted to look at them on patty paper, that's what we did on standard 3. This angle would translate right down here and make a pair of corresponding angles that are congruent. And then we also know that these two angles would correspond. I'm going to go ahead and just use angle A because both of these triangles share angle A. So I could say the big triangle ABC is similar to triangle AEF by the angle triangle similarity. So if two angles in triangles are the same, then those triangles are going to have the same shape, not necessarily the same size, but they'll be the same shape, which means all three pairs of angles are congruent that correspond, and the sides are not necessarily congruent, but they are proportional. So when we were learning this section, we would say that angle A would be congruent to angle A in the big triangle and the small in the big triangle. Angle AFE, this angle, is congruent to angle C, this angle, because of the corresponding angles. And then by the triangle sum theorem, or by using this pair of corresponding angles, angle AEF, this one up here, is congruent to angle B. So all three pairs of sides are congruent. And all three pairs of angles are congruent. And these sides are not the same measurement, but the ratio of those sides are the same. So if I take the ratio of A to B in the big triangle and compare that to the ratio A to E in the small triangle, if you look, they're in the same position on our similarity statement, then that's going to be the same ratio as this big segment, BC, and this small segment that corresponds, EF. And it's going to be the same ratio as A to C, this big segment, over A to F. So those ratios are the same. So that's what it means by the angles are congruent and the sides are proportional. So I'm going to put some numbers in there. I'm going to say that this side is, this part right here is 5, this part right here is 2. So we know that the entire segment A to E is 5 plus 2, which is 7. So if I know that this side is 4, then I can now find the length of AB. So our scale factor, if we're going from the small triangle to the big triangle, is the big value over the small value. Remember, you're putting the whatever your image is, your new figure, that value goes on top. So the scale factor in this case is going to be 7 over 5. That's the big side length and the small side length. So if I carry that proportion on to this side, the big value is AB, and the small triangle's value that corresponds to that is 4. So we set up many different proportions like this. And now it's a matter of doing our algebra to cross multiply and solve. So now when I cross multiply and solve, I would have 7 times 4 is equal to AB times 5. So 28 would equal to AB times 5. And we would divide both sides by 5 and get 28 divided by 5 as AB. So some of you may want to put that in your calculator. And if it's an actual decimal that ends, you can leave it as a decimal, but if it's not, then you would want to just leave your answer as a simplified fraction. So, or 5.6 units. So 5.6 units would be this value here. And we could always find this value by doing 5.6 subtract 4 would give us this value right here. So this is angle similarity, and we know that those sides are proportional. Now, one more fact that we learned that is sometimes useful is a line parallel to a side of a triangle cuts the sides proportionally. So if EF is parallel to BC, that would mean that the ratio 5/2 is the same as the ratio 4 over this measurement right here. So if I did 5/2 and 4 over, if we took this 5.6, subtract 4, what did we get for this measurement right here? We get 1.6, right? So you can use it to find a missing value, or we could verify that these are parallel that way. Both ways are fine. So you could cross multiply and ask yourself, is 5 times 1.6 the same as 4 times 2? 5 times 1.6 is 8. 4 times 2 is 8, so that is true. Or you can look at your calculator. 5 divided by 2 is 5.2. 4 divided by 1.6, that's, oops, I do it upside down. 5/2, 4 over, no, that's right. There we go. So there's our 5 divided by 2. I punched it in my calculator wrong. 5 divided by 2 gives you 2.5. 4 divided by 1.6, thank you, also gives you 1.5. So that's another way to verify that those sides are proportional. So 2.5 does equal 2.5. So that would mean that side EF, segment EF, is parallel to segment BC. All right, and we'll have some practice problems to show understanding of those.